afternoon and good evening, everyone. I'm Cassie Wu from Amazon, and I'm thrilled to be here at Best of CVPR 2026 to share the work on HyperRealm, which has been recognized with the Industry Innovation Award at CVPR 2026 in Denver, Colorado in June. And first of all, I want to thank Voxy51 for organizing such an amazing platform, and thanks to Jimmy and the team for hosting this amazing webinar event so that we have an opportunity to showcase the latest research work and engage with the broad community. Really appreciate it. Today, I will show how we fundamentally re-image the vision language models by replacing Euclidean geometry with hyperbolic space. It's a very powerful change that unlocks better hierarchical understanding across image and text. And you can find the description of my paper and the bio on Voxy51 event link. And here I also pasted a link in QR code to hit me. And this is a picture where I was hosting this certificate at CVPR. And here is our journey for this talk. We'll start with the core problem, why standard vision language models struggle with hierarchical data. Then I will give you an intuitive understanding of hyperbolic geometry before diving into our methodology. We'll examine comprehensive experimental results across 18 datasets, explore some fascinating theoretical insights, and conclude with real-world impact. First of all, let's look at the introduction. So let's start with a fundamental question. How do current vision language models represent hierarchy? Consider a simple example, an image of a dog. This could be described as animal at a very general level, and mammal more specifically, dog even more precisely. Our golden retriever playing fetch at the finest granularity. This is a natural hierarchy, a tree structure. But here is a problem. Models like CLIP embed both the image and the text in Euclidean space, and Euclidean space has a critical limitation. It grows polynomially. As hierarchy deepens, you'll run out of room to faithfully represent these tree-like relationships without massive distortion. Think of it like trying to fit an exponentially growing tree into a fixed size box. You have to either crush the structure or lose the fine-grained distinctions. Why does this matter beyond academia? Because a real-world deployed system faces a hierarchy problem every single day. In e-commerce, we have product taxonomies, electronics to laptops, gaming, laptop to specific models with different configurations. When customers search for laptop, we need to understand why they want to have general laptop content or they are looking for something very specific. And in medical image, for example, the disease hierarchies, condition to disease to subtype to severity stage. Misclassifying at the wrong level isn't just inaccurate, it can have serious consequences. Remote sensoring also requires understanding geographic hierarchies, urban area, residential to single-family homes, special to specific architecture styles. All of these applications exhibit natural tree-like structures, and the current VLMs flatten them, losing critical information. In VLMs, Euclidean embeddings cause these specific problems. First, suboptimal fine-grained discrimination, and second, semantic drift, and third, downstream task failures. And the math is very clear. Euclidean space grows as n squared, but hierarchies grows exponentially. You cannot faithfully embed an exponential structure in a polynomial space without severe distortion. This brings us to our central research question. Can we design a vision language model that naturally preserves hierarchy relationships while maintaining semantic alignment? The keyword here is naturally. We don't want to bolt on hierarchical constraints as an afterthought. We want the geometry space itself to respect hierarchy. And that's exactly what HyperRealm does by switching from Euclidean to hyperbolic geometry. Let's take a glance at the background. The key insight is hyperbolic space grows exponentially as you move away from the origin. Imagine you are standing at the center of a disk in Euclidean space. As you walk outward, the circumference grows linearly with your radius is predictable, steady. But in hyperbolic space, the circumference grows exponentially. Each step upward gives you dramatically more room. It's like the space itself expanding the farther you go. Why does this matter for hierarchies? Because hierarchies grow exponentially too. A tree with branching factor 3 has 1 root, 3 children, 9 grandchildren, 27 great-grandchildren. That's exponential growth. Hyperbolic space matches the growth rate of hierarchical data. That's the magic. And let's see this visually. On the left, we have a tree embedded in Euclidean space. Notice how cramped it gets at the leaves. The nodes are forced close together, and we lose the ability to distinguish fine-grained categories. On the right, the same tree in hyperbolic space. Look at how naturally it fits. General concepts near the center, specific concepts spread out near the boundary. The distance accurately reflects hierarchical relationships. This isn't just aesthetically pleasing, it's mathematically optimal. Hyperbolic space achieves logarithmic distortion for trees compared to square root distortion in Euclidean space. That's a massive difference for deep hierarchies. For HyperRealm, we use the Poincaré model among all the options of the hyperbolic models. Let me explain why this is the right choice. The Poincaré is a unit disk. Everything lies inside a circle of radius 1. It has 3 key properties. First, it's near the center, and it behaves almost like Euclidean space. And second, as you approach the boundary, distance stretches exponentially. And third, the model provides a conformal mapping, meaning it preserves angles. This gives us well-behaved gradients during optimization. Think of it as a fisheye lens view of an infinite space. We compress infinity into a bounded disk, but the geometry still respects the exponential structure we need. For those wanting the mathematical details, we use hyperbolic distance based on Mobius addition, and we map between Euclidean and hyperbolic space using exponential and logarithmic maps as the origin. The key equation is shown here, but I won't derive it. What matters is that this metric naturally encodes hierarchies through distance, and we have well-defined operations to move between space during training. Full details are in the paper, including curvature analysis and Riemann metric derivation. Now let's take a look at the methodology. Let's see how HyperRealm actually works. The architecture builds on CLIP. Start with standard encoders. We use vision transformer for image and a text transformer with bed pair encoding. Exactly like CLIP, this means we benefit from the scaling work done on this architecture. And what is different? First, after the encoders, we add learnable scaling parameters, lambda image and lambda text. This prevents numerical overflow when we map to hyperbolic space. And second, we apply exponential maps to project embedding from Euclidean space onto the Poincaré ball. This is where the magic happens. We are moving from flat space to curved space. And third, instead of cosine similarity, we compute hyperbolic distances. This respects the geometry. You cannot just dot product in curved space. And fourth, we optimize two objectives simultaneously, contrastive laws for semantic alignment and our novel entropy-driven entailment laws for hierarchical structure. I will dive into this part right after this. This dual objective approach is crucial. We preserve CLIP's semantic alignment while adding hierarchical awareness. To zoom in embedding pipeline, the first step is Euclidean encoding, and the second step is learnable scaling, third step exponential map, and the fourth step is hyperbolic embeddings. One beautiful property is that this transformation is differentiable, so gradient flow smoothly during backpropagation. We can train with standard optimizers. The first component of our training objective is contractive loss. This is what gives us semantic alignment. And for a batch of n image text pairs, each pair has one position match n plus one negative sample. And y negative distance because we want to maximize similarity, and in hyperbolic space, smaller distance means greater similarity. And crucially, this preserves what CLIP does well, semantic alignment across modality while operation in a geometry that respects hierarchy. The loss has two symmetric terms, one treating image as queries and text as targets, the other reversed. Now let's take a look at the key innovation part, the entropy-driven entailment loss. This is what gives HyperRealm is hierarchical awareness. The core idea is more specific concepts contain more information than general concepts. Golden retrieval playing with a tennis ball contains all the information of dog plus additional details. We can quantify this using entropy. For any embedding X in our shared space, we compute entropy in this formula. And think of this as mirroring information content of specificity of the concept. General concepts have low entropy, and the specific concepts have high entropy. Here is a crucial insight. We don't assume a fixed direction of entailment. Previous work like Maru assumed the text always entails image, but that's not always true. Sometimes an image is more general than its caption, sometimes more specific. Instead, we dynamically determine entailment direction at the instance level by comparing embedding entropies. Lower entropy equals more general and equals the entailer. And the higher entropy equals more specific equals the entailed. This adaptive mechanism is far more flexible than fixed assumption. Once we have determined entailment direction via entropy, we enforce it using an entailment cone loss. Here is a geometry intuition. We have the first term and the second term listed in this formula. Why does this work? Because in hyperbolic space, partial order relationships correspond to containment in cones. If A is more general than B, B should lie within A's cone. And remember, we determine A and B adaptively based on entropy, so this works for any instance, regardless of whether image or text is more general. Our complete training objective combine both laws, the contractive loss plus lambda times entailment loss. The dual objective framework simultaneously optimized for semantic alignment and hierarchical consistency. The beauty is that both objectives work together harmoniously. They do not fight each other because they are capturing complementary aspects of multimodal relationships. Next, let's take a look at the experiment and the results. Now let's see if this actually works. We conducted an extensive evaluation to validate HyperRealm. 18 diverse datasets spanning multiple domains, and the general objects dataset including Cipher 10, 100, STL10. Fine-grained categories include CUB 200 bird species, and Oxford flowers and pets. And the scene understanding includes SUN 397, and satellite imagery includes Euro SAT, and so on. We also tested on medical domain as well to cover the diversity of dataset to validate our methodology. And the three model sizes are used as backbones. This tests whether benefits come from geometry, inductive bias, or just a parameter count. And the baseline, we compare against the Euclidean CLIP and Maru, which use the Lorentz model hyperbolic embeddings. This isolates the contribution of our Poincaré model. And the test includes zero-shot image classification, image text retrieval. And here are major results on zero-shot image classification across 18 datasets and 3 model sets. HyperRealm consistently outperforms both CLIP and Maru. If we double-click the per dataset performance, we can see that we We can highlight that the COB 200 has a 1.4% improvement. That is a 4-level biological hierarchy with 200 fine-grained bird species, and Cepher 100 has an improvement around 3% gain. This dataset has 20 superclasses with 5 subclasses each. And for EuroSAT, which has a 5.2 improvement, and that is the largest gain. This is a satellite land use classification with geographic hierarchies. Okay, so next, beyond classification, we evaluate image text retrieval, a critical task for real-world applications like e-commerce search. Coco and HyperRealm shows a consistent improvement across our metrics for image-to-text retrieval and the text-image retrieval, and we evaluate recall at 5 and 10. And so we conclude through the ablation studies to understand what drives performance. We perform a grid search over entailment loss weight lambda and regularization strength lambda reg, evaluating on Coco and Cepher 100. And the key finding is that the best performance happens at lambda equals 0.1 and lambda reg equals 0.1. And the performance is relatively stable around this sweet spot. It's not hypersensitive to exact values. This confirms that both loss components are necessary and work synergy. You need semantic alignment and hierarchical structure. One without the other is suboptimal. Now let's think about the theoretical insights. We can view hierarchical relations through an information theoretical lens. The key principle is that the special concepts contain all information of their parents plus additional details. For example, golden retrieval contains all information of dog. It is a dog plus special breed characteristics. And mathematically, it is a child is larger than parents and where H is entropy. Here is a beautiful connection. In our shared embedding space, we can measure information content via entropy. This gives us a common currency to compare images and text. And the low entropy means general, and the high entropy means specific concepts near the boundary. Distance preserve information theoretical relationships. It's a principled grounding of multimodal hierarchies in information theory and differential geometry. We might wonder why Poincaré ball. So there are 3 advantages of Poincaré ball over a Lorenzo model. The first is a representation capability, and the second is numerical stability, and the third is geometry properties. It has more stable optimization, better gradient flow, and a smoother loss landscape. Our empirical results confirm this, and we consistently outperform Meru across hierarchical retrieval tasks, validating that this theoretical advantage translates to practical benefits. To quantify the representation capability more precisely, we can see that the Lorenz hyperboloid mod needs dimension around d, and the Poincaré ball needs dimension d over logarithmic of d, so it's near linear. And this means we can faithfully represent deeper hierarchies in lower dimensional space, critical for computational efficiency and generalization. Now let's take a look at the conclusion. First, hyperbolic multimodal embeddings, and we represent image and text in a shared Poincaré ball, naturally preserving tree-like hierarchical relationships inherent in multimodal data. And the second, the entropy-based partial order inference. And third is a comprehensive empirical validation through exhaustive datasets across different domains. Fourth is a theoretical grounding. We also provide information theoretical justification connecting entropy, hierarchical structure, and hyperbolic geometry. So together, these contributions establish hyperbolic geometry as a foundational framework for structured multimodal understanding. So HyperRealm address critical real-world challenge across e-commerce, medical imaging, scientific literature, and educational content. Why this matters? Now, as AI systems increasingly operate in structured, heterogeneous real-world environments, geometry-aware representations provide a principled foundation. HyperRealm demonstrates that respecting the geometry structure of the data leads to better performance. Is technology ready for deployment? Thank you for listening. HyperRealm demonstrates that by carefully choosing our geometry foundation, replacing Euclidean with hyperbolic space, we can build a VLM that naturally understands hierarchical relationships. You can scan the QR code to take a deeper look of our paper with additional results. And now I'm happy to take questions.